yet, but I'll let you know when I do. I should get it in a day or so. Secondly, I will put a practice test on the web. I think I'll get that done tomorrow. And we'll discuss that on the Wednesday. We'll have a review day Wednesday next week. So I'll go over that and anything else that's causing problems. Okay, so last time we broke off, just stated a theorem. Which said the following. So let me write it down again. This was theorem 2.5. Said that f of x is continuous on the interval -1, 1. Then there's a series, sum from 0 to infinity, a n x to the n, has radius of convergence 1, and all of the ANs are positive, provided you go far enough down the line. So eventually, all of the ANs are positive. And the conclusion was, if f of x is equal to the sum from 0 to infinity a n x to the n, for x in the open interval -1, 1, then the series converges uniformly to f of x on the closed interval -1, 1. So what this theorem is really dealing with is the endpoints. When you have a power series, normally all you know about convergence is the open interval -r to r, the radius of convergence. So under the extra hypothesis that on the open interval it's actually converging to a continuous function, then this will force convergence at the endpoints, and we'll get the extra thing that it converges uniformly to the function. So let's prove this. Now, the hypothesis is that the coefficients are eventually non-negative. So in case 1, I'm going to assume that all ANs are non-negative. It'll be easy to deduce the general result from this. So we first prove that sigma an from 0 to infinity converges. Well, if not, since it's a series of non-negative terms, there are only two possibilities. Either it converges or it sums to infinity. So if not, then sigma an is infinite. Which means that the partial sums grow without bound. So given any number, capital M, exists capital K, so that the sum from 0 to capital K of an is at least capital N. Now, the limit as x goes to 1 from the left of the sum from 0 to k and x to the n. Since it's just a finite sum, I can take the limit inside, and as x goes to 1 from the left, that converges to the sum 0 to k a n. That is equal to the sum 0 to k of the a n's, and that is at least m. Since this is a polynomial, it's nice and continuous, so as long as I'm close enough to 1, I can make this at least as large as m over 2. So there exists some delta greater than 0, so that the sum from 0 to k, an x to the n, is at least m over 2 for x in the interval 1 minus delta to 1, the open interval. Well, on this interval, the sum from 0 to k of an x to the n is less than or equal to the sum from 0 to infinity an x to the n, because all terms are non-negative, so if I add more of them, it just gets bigger. But we have the hypothesis that on the open interval -1 to 1, this converges to f of x. So this is equal to f of x. And so what we conclude from that is that f of x is greater than or equal to m over 2 on the interval 1 minus delta to 1, the open interval. However, the function is continuous on the closed interval, and so it's bounded. So since f of x is continuous on the closed interval -1, 1, it is bounded by some constant, which I will call m0. And therefore, m over 2 cannot exceed m0. was a fixed number coming from the function, and m was just some arbitrary large number. Since m is arbitrary, this gives a contradiction. And it contradicts the assumption that the sum from 0 to infinity an was infinite, and therefore that sum is finite. Therefore, sigma an is finite. Now we can apply the Weierstrass M-test, since the absolute value of an x to the n is less than or equal to an on the closed interval -1, 1. The Weierstrass M-test, here's my sequence of numbers that's convergent. The Weierstrass M-test gives uniform convergence of sigma an x to the n on the closed interval. So we've managed to pass from the open interval to the closed interval and also get uniform convergence. So let's call it summed something else. Let g of x be equal to the sum from 0 to infinity an x to the n, x in the closed interval -1, 1. So it's the uniform limit of polynomials, partial sums, and so it's continuous. G of x is continuous on the closed interval -1, 1. And because we know that on the open interval -1, 1, the series converges to f of x, this must equal f of x on the open interval -1, 1. But if you have two continuous functions that agree on an open interval -1, 1, then they will agree at the endpoints too, just by taking limits. So therefore, by continuity of f and g on the closed interval -1, 1, we have that f of x is equal to g of x, which was the infinite sum an x to the n from 0 to infinity, now on the closed interval -1, 1, with uniform convergence. So that is what we wanted. So the special hypotheses on the coefficients an, that they should all be non-negative, allows us to conclude that we can extend the convergence from the open interval to the closed interval. Now the general case we can get easily from this. So case 2, finite number of negative coefficients, and so there will be a last one. So there is a number n0 so that an is greater or equal to 0 for n greater or equal to n0. So then we can write the sum. I'll just split it up into a first finite piece. That's the piece where some of the ANs could be negative, plus the remainder where we now know that all the coefficients are non-negative. So if I take that piece to the other side, f of x minus the sum 0 to n0 minus 1, an x to the n, is equal to this power series where the power series on the right-hand side has only non-negative coefficients. So this puts us into case 1, not with the function f of x, but with the function f of x minus one of the partial sums. So apply case 1, we get that the sum from n0 to infinity, an x to the n, converges uniformly on the closed interval negative 1, 1 to the function f of x minus the sum from 0 and 0 minus 1, an x to the n. And now just rearrange the equation. So therefore, the sum from 0 to infinity, an x to the n, converges uniformly to f of x on the closed interval negative 1 and 1. Let's just note the theorem remains true if all the ANs are negative eventually. Because all you have to do is put a minus sign in front of everything. Look at negative f of x is equal to the sum from 0 to infinity, negative an x to the n on the open interval negative 1, 1. So just multiplying by negative 1 puts us into the theorem, where now all the coefficients are eventually non-negative. Okay, so I want to apply this to a specific function. And the reason we're going through all of these calculations is this, let me just mention there are two difficulties with Taylor series. You learn Taylor series in calculus. For f of x, the series is the sum from 0 to infinity, the nth derivative of the function evaluated at 0 divided by n factorial times x to the n. So assuming that you have a differentiable function, infinite differentiable, you can compute the series. So two questions arise. That will have some radius of convergence. If the radius of convergence is r, then all we know in general is that the series converges on the open interval negative r to r. Question 1, does it converge to the function that we used to generate it? Question 1, does Taylor series converge to f of x on negative r. And question 2, which is basically the one that I've tried to deal with in this theorem, is does it converge to f of x on the closed interval, negative r to r? The answer to this is not always, in both cases. When you're learning calculus, all the series you ever compute do converge to the function. And this is true for most nice functions. E to the x, sine x, cosine x, all the standard functions of calculus. Their Taylor series really do converge to the function used to generate them. But there are some bizarre examples out there where this is not true. So let me mention briefly two examples. The first of them, question 1 has a negative answer. And as I said, you've got to cook up something quite strange in order to get that. But what it does tell you is you cannot take it for granted that the Taylor series converges to the function. So here's a function where it doesn't work. So e to the negative 1 over x squared when x is not 0, and 0 when x is equal to 0. So as x tends to 0, 1 over x squared tends to infinity. So e to the negative 1 over x squared tends to 0. So it's a nice continuous function at the origin. Now you have to use the original definition of derivative in terms of limit h goes to 0 of the quotient. But I'm not going to do this. But with sufficient effort, converges for all values of x, but unfortunately it converges to 0. So here's an example of a function for which you can generate a Taylor series, but the Taylor series does not converge to the given function.
If you choose a nearby point by 0, does it then converge to the function?
Yes, 0 is the main problem with this function. If I compute a Taylor series, say at x equals 1, in powers of x minus 1, everything will be fine. The pathology of this function occurs at 0.
So how many such points can exist for a given function, where if you pick it and then you expand the Taylor series about that point, it won't converge to the function?
Well, I could take linear combinations of this with translation, and so I could probably get this to happen at every rational, for example. So I could get a countable number of points where it could happen. So if you really go looking, things will be bad. If you go looking for trouble, you will find it.
That's pleasant.
So this really is an exceptional function, but it exists, and therefore you cannot just say, let's write down the Taylor series and it converges to the given function. That is not guaranteed without further work. So this kind of thing is too hard to discuss in elementary calculus, and so you never see it. But these things do exist. And, question 2. Question 2 has a negative answer. If you start from the series 1 over 1 minus t, which is 1 plus t plus t squared, and so on, that is fine for absolute value of t less than 1. And if you put t is equal to negative x squared, then you find that 1 over 1 plus x squared is 1 minus x squared plus x to the 4th minus x to the 6th, and so on. And that is good for the absolute value of x less than 1. So here we have convergence of the Taylor series to the function 1 over 1 plus x squared, at least on the open interval. This has radius of convergence 1. Now, there's nothing wrong with this function. It's perfectly well defined and continuous at negative 1 and 1. But the Taylor series will not converge at either point. So 1 over 1 plus x squared is continuous on the closed interval negative 1, 1, and in fact on the whole real line. But the series does not converge at x equals plus or minus 1. So here's a case where you have a nice continuous function, you compute its Taylor series, you get convergence on the open interval for the radius of convergence, but you cannot get it on the closed interval. Notice this is not covered by the theorem because the coefficients alternate in sign. Plus minus, plus minus. So that's why I've called these difficulties, simply because we cannot rely on having it true all the time. this is not continuous on the closed interval negative 1, 1, because you've got a problem at t equals 1. And as you can see, the coefficients are 1, 1, 1, 1, 1, 1, 1, so they sum to infinity. So this substitution is just to make sure that I am now dealing with a nice function. Okay, so the example that I want to apply this to, there's only one function that we're going to apply it to, but it's an important one for what we're going to be doing, and that is the function f of x is equal to the square root of 1 minus x, which is 1 minus x to the 1/2 power. The only problem you have with that function is when it goes, where the quantity under the square root goes negative, and so this is defined for x greater than or equal to negative 1. In particular, it is continuous. No, x greater than or
Less than or equal to 1.
yes, defined for x. Get it right at the fifth attempt. It's defined for x less than or equal to 1. In particular, it is continuous on the closed interval negative 1, 1. So what we will need is its Taylor series. So we need to compute a few terms, and then we'll see a pattern emerging. So first of all, when I plug in 0, I get 1. The first derivative is, I'll pick up a negative sign from under the square root, so I'll have negative 1/2, 1 minus x to the negative 1/2, and f prime at 0 is going to be negative 1/2. The second derivative, now this time I have both a negative exponent and I'll pick up a negative 1 from inside, and so the sign will not change after this. So I'll pick up a negative half, so that will be negative 1 over 2 squared, 1 minus x to the negative 3 over 2, and the second derivative at 0 is negative 1 over 2 squared. Yes?
Why is it negative?
I had a negative here. I pick up a negative from here and another negative when I differentiate the inside.
Yes.
And so I will stay with a negative. And that's going to be true. Now that all the powers here are negative, I'll pick up one negative there, one negative from the inside, and so all of these will be negative from now on. So the third derivative is negative 3 over 2 cubed, 1 minus x to the negative 5 over 2. And so the third derivative at 0 is negative 3 over 2 cubed. And one more. The fourth derivative at x is negative 5 times 3 over 2 to the 4th, 1 minus x to the negative 7 over 2, and the fourth derivative at 0 is equal to negative 5 times 3 over 2 to the 4th. And that's it. Now, next time you differentiate, you'll pick up a 7 on top and another 2 down below. So the denominator is going up in powers of 2, and up top we're multiplying by the next odd integer. And so in general, the nth derivative at 0 is going to be the product of the numbers 3 times 5 times 7 times. Now, in order to go up by 2's, it'll have to be 2n, and then when I plug in 4, I ought to get 5, so that should be negative 3. So that will generate a sequence of odd integers, and it will end for f4 at the right place, namely 5. And down below, I will have 2 to the n, and then I need a negative sign out front. So that will be the nth derivative. And this will be true as long as n is greater or equal to 2. So there are 2 exceptional ones at the beginning, but then a pattern emerges for n greater than or equal to 2. Now, whenever you have a product of odd numbers like this, it looks like a factorial, but it isn't quite. What we can do is make it into a factorial by putting in all the even numbers. And the way I want to write that is okay, so this is negative. Put in all the even ones. 2 times 3 times 4 times 5 times 7 times all the way up to 2n minus 3. I have 2 to the n, and then I have to put in the even ones down below that I put in upstairs. So that's what that looks like. And now, if I pull out all the 2's that I have here, how many do I have? I have n minus 2 of them, so that's on top. I have 2n minus 3 factorial. Down below I have n minus 2 terms, so that's 2 to the 2n minus 2. And what I'm left with is 1 times 2 times 3 up to n minus 2. So n minus 2 factorial. Right. And therefore, the Taylor series is this. So I have 2 exceptional terms. So it starts 1, and then minus a half x. And then when I get to n at least 2, I can use this general formula. So it will be minus the sum from 2 to infinity. This coefficient, I've already taken out the minus sign. So 2n minus 3 factorial divided by 2 to the 2n minus 2 times n minus 2 factorial but then I have to divide by n factorial and multiply by x to the n. So that is the Taylor series. And what I would like is that that actually converges to my original function, square root of 1 minus x, at least on negative, closed interval negative 1 to 1. And I would like it to converge uniformly. So to get the radius of convergence, let's use the ratio test to get the radius of convergence. So you look at the ratio in absolute value of the n plus first term to the nth, and that is the n plus first term. So if I replace n by n plus 1, I will get 2n minus 1 factorial divided by 2 to the 2n times n minus 1 factorial n plus 1 factorial x to the n plus 1. And then dividing by the nth term, I'll have an x to the n, a 2n minus 3 factorial down below, 2 to the 2n minus 2, n minus 2 factorial, n factorial. The great thing about factorials is that they usually cancel down to almost nothing. And that's the case here. So when I cancel the 2n minus 1 factorial with 2n minus 3 factorial, what I'm left with is 2n minus 1, 2n minus 2. When I cancel the n factorial with the n plus 1 factorial, I'm left with an n plus 1. And the n minus 2 factorial with the n minus 1 factorial leaves me n minus 1. The powers of 2 cancel down to a 4 down below, and I'm left with a single power of x. Now what that is basically 4n squared divided by 4n squared plus lower order terms. So that ratio tends to 1, and so this tends to absolute value of x as n goes to infinity. So the ratio test tells you as long as the ratio tends to something that's less than 1, we will have convergence. So therefore, the series converges for the absolute value of x less than 1. Notice, too, that once you get past the first couple of terms, the sign on the coefficients is now uniformly the same. It's always negative. So that was the situation of that theorem that I proved. So, what is left to do? What we have to show is that the Taylor series converges to the square root of 1 minus x on the interval negative 1 to 1, and then the theorem will tell us that we actually have uniform convergence on the closed interval negative 1 to 1, which is what I want. So explain how this will go. I don't think we'll have time to do it today. So let g of x be equal to, let me just call it the Taylor series. On the open interval negative 1, 1. What we want is that f of x is equal to g of x on the interval negative 1, 1. And then theorem, whatever it was, 2.5, tells us that the series converges uniformly to square root of 1 minus x on the closed interval negative 1, 1. Right now, if you plug in x equals 1, it is not at all clear that that series converges. So there is a problem to be dealt with. So the way this is going to go is as follows. So if we believe or hope that g of x is equal to 1 minus x to the 1 half, then we believe that 1 minus x to the negative 1 half g of x should be equal to 1, just multiplying through by 1 minus x to the negative half. And consequently, we should believe, now since g of x is defined by a series, we know it's differentiable term by term. So we're going to believe that the derivative of this is 0. Now when you differentiate, you get 1 half 1 minus x to the negative 3 over 2 g of x plus 1 minus x to the negative 1 half g prime of x should be 0. And consequently, multiplying through, we would also believe that g of x plus twice 1 minus x g prime of x should be 0. Now, all of these steps are reversible. If I have the last one, then I have the one before it, and that is simply the derivative here. Now, I would have to be careful. I would just know that it's equal to a constant. But then by plugging in x equals 0, I can find that the constant is 1, and then I'll get back to here. So in fact, this is what we have to verify. If we can show that the Taylor series satisfies that last equation, then g of x will in fact be the square root of 1 minus x. Anyway, we're out of time for today. I'll deal with that on Friday. It's not difficult, it's just a question of taking the power series and working out both of these things.